Okay, let's go to the implementation of the factorial problem. To define this recursive problem, you have to find out the base cases and the recursive part. We have already done it here. So the base case is basically 1. So when we reach to the number 1, we cannot divide it furthermore. And the recursive function, if you define it n terms, should be n into n minus 1 factorial. Okay, so let's code it. Here I have already the main class defined. Now we have to define this function. So let's write it down. Let's call it fact. It will take an integer number. The method should have a return type, so let's look at kind of return types it has. If you look at the diagram, when we reach to the value 1, we have to go back with a integer value. Okay, so the type of my method should be integer, so integer, and we have to make it static because we are in the same class. Okay, so let's define the base cases. First, base case. So if my value is 1, which means the value of n is 1, I have to return 1. Otherwise, we have to divide the problem. So let's divide it. Return n into fact of n minus 1 factorial. That's it. So I want to print it so that you can actually understand how the values goes on. Value of n inside f, and we'll go to the step for the else statement so that we can actually visualize inside the else. Okay, this is the recursive word. Now we are going to call it. Okay, I'm going to print it directly by calling it inside the print statement. So make it n. Okay. Sorry. Okay. So if we run it, we can see the inside the function 5 is inside my else statement because we can further divide it. So on 4 is also inside the else statement. 3, 2, so on are all inside the else statement. Whenever we go to if is when we reach to the base case, which is 1. Okay, so this is the basic definition of the factorial problem. Okay, so from the mathematical definition, we know that factorial of 0 is also a valid case. In my programming or my recursive function, there is nothing called 0 or nothing called something which deals with 0. So let's see what happens if I don't define this. If we compile and run it with the same code, you see they're going negative, negative, but it never stops. So we can say we have missed a very smaller case, which is even though the program will execute forever, so we have to write it as a base case. Okay, so what we have to do, we have to define it as a base case because n equals to 0 also returns 1 from the mathematical definition. So we cannot mess it out. So we have more than one base cases. So remember, when you write a recursion, you must write all the base cases. If you miss any base case, your recursion will go forever and ever. It's not gonna stop, and for a long instance, it's gonna overflow your RAM or your memory. Okay, let's take a look to another problem which can be solved using recursion. All of you know how the Fibonacci sequence works, right? So we have 0 1, then we have the summation of the previous two. So 0 1 plus will give me 1, 1 plus 1 gives me 2, 2 plus 1 gives me 3, 2 plus 3 gives me 5. So the next sequence is always the summation of the previous two sequence, right? So here we can how we can formulate this as a recursive way of thinking. So we have to have the base cases. In this case, the base case, the starting of the sequence are the base cases. So 0 and 1 is my base case. What about the recursion? So recursion is starting from this 1 is the summation of the previous two. So you can say that f of n, right, if we define it as in terms of f, n is the summation of the previous number, which is n minus 1 plus n minus 2. Can we do that? Right, f of n, or we can call it fib, so this doesn't look like a function. Okay, so for 3 is should be 2 and 1. So if we consider n as a position of all the sequences, okay, so this is my position 1, this is my position 2, this is my position 3, 4, and so on. So this will represent the position 5. The 3 will be the position 5, which will lead to the summation of 2 and 1, and so on. So this is my recursive definition. These are the base cases. Okay, let's take a look to the let's do the recursion diagram, where you have to find out the Fibonacci of like 6 position number of the Fibonacci sequence. So here how we can find it out. 6 means n minus 1 means fib of 5, n minus 2 means fib of 4. So this can also be divided, and we go further till we get to fib of 1 and fib of 0. Fib of 1 and fib of 2, which cannot be further divided in this case. So let's take a look to this example. Okay, so here I have defined the function fib, where you can see the returning time should also be integer, because it's returning a number which will be the summation of the previous two. And so the base cases are when my n value is equals to 1 or n value equals to 2, I'm gonna return okay, so this is different, because for n equals to 1 it should return 1. Okay, let's consider the position starting from 0, which will lead for more easier version of it, or we can consider it is 1 and 2, that's fine. Okay, and here we return 0. These two are base cases. Otherwise we are going to return fib of n minus 1 plus fib of n minus 2. Okay, that's it. Let's get into this example. Compile. It gives me 3, and according to our problem, 1 2 3 4 5, this should give me 3. Let's look if it gives me 13. 1 2 3 4 5 6 7 8. Let's make the value of n as 8. It should give me 13. Okay, 13. So this works. We can consider the position starting from 0 as well if you want, instead of 1. So we can call it 0 position, 1 position, 2 position. So in that case we have to rearrange the values of n, but that's fine.